Hi, let's talk about numbers. Physics deals with numbers a lot. In fact, I would argue that the foundation of physics is finding ways to quantify aspects of physical systems that we find interesting, experimentally exploring the relationships between those quantities, and then inventing mathematical conceptual models to explain the relationships between those that we see. That's pretty much the whole game of physics summed up right there in that sentence. So if you're going to do physics or chemistry or computer science or biology or pretty much any mathematical field, you're going to need to get pretty good at handling numbers. That's what this unit is all about. The single most important thing to know about numbers in physics is that numbers are not just numbers. Unlike most of the math classes you probably had, in physics, numbers represent some physically meaningful quantity. And that is actually a huge deal. Here are some questions you should ask yourself about any numerical quantity you encounter in physics. 1, what's it called? 2, what kind of quantity is it? 3, how big or small is it? 4, how precise is it? And 5, most importantly, what does it mean? So if you encounter just this in a physics context, that doesn't tell you very much, does it? But if I dress it up a little bit like this, now you have a lot more information to interpret it. This thing over here is a label. It tells us what variable, what symbol we're going to use in our algebra to represent it, so you don't have to write the whole thing every time. The choice of m usually means the quantity is a mass. That's not a hard rule, but it's a convention. The subscript Pluto tells me that this quantity has something to do with Pluto, probably the planet, not the Disney character. So this choice of label tells me that this probably describes the mass of the planet Pluto. And that's clear labeling. It communicates a lot fairly compactly, and it helps me remember what this quantity means, so I don't have to keep reminding myself or figuring it out or looking it up. Yeah. This part here, plus or minus 0.003, is called the uncertainty. It says that the real exact value that I can't possibly know is somewhere between this plus this, 1.306, and this minus this, 1.300. And that's all the information I have. Sometimes we don't write the uncertainty explicitly. Sometimes we leave it implied and don't show it. If I just saw this here without the plus or minus, I would interpret that as saying that the last digit shown is a little uncertain, a little wishy-washy. I can be pretty sure about the 0. I'm not so sure about the 3, and I really don't know anything about the digits that come after. So I would say, without that, that it might be plus or minus 0.001, plus or minus 0.005, something like that. But I'm in the right ballpark. Now, if you, in the physics course, write down a number like this, 1.30329917648401 ... I know that one of two things is true. Either you just made the most stunningly precise measurement or calculation in the history of physics, or you mindlessly wrote down the numbers your calculator was showing you without thinking. If you only put in numbers with about 4 digits of accuracy, that's all you're going to get out. Anything else is just fiction. Don't do that. OK. This part here says that everything in here is to be multiplied by 10 to the 22nd power. That means 10 times 10 times 10, 22 times. That's equivalent to moving this decimal point and this one over 22 places and padding out with zeros as necessary. Except this is a whole lot easier to write. It's called scientific notation. We will use it a lot. This part here is called the unit. And it's really important. In fact, it's so important that we're going to have a separate video on that coming up next. Okay. So back to our list of questions about the quantity here. Let's hear. What's it called? M sub Pluto, or, which is probably a short for the mass of Pluto. What kind of quantity is it? The M suggests I'm talking about a mass, and the use of kilograms for the unit confirms that this is some kind of a mass. What's its scale? How big or small is it? Round about 10 to the 22nd kilograms. That is big. That's about 1 billion times my mass. What's its precision? Plus or minus 0.003 times 10 to the 22nd kilograms. In fact, that's about, let's see, 0.003 divided by 1.303 is about 0.0025, which is 1/4%. So the room for error, the room for uncertainty, I should say, in this number is about 1/4%. That's fairly precise. And most importantly of all, what does it mean? That's up to you in whatever context you encounter this number. Maybe it means that even a dwarf planet, too small to be considered a real planet anymore, is still really freaking huge, at least compared to, me. Maybe it means that compared to Jupiter and Saturn and Uranus and Neptune, it's actually really small. Maybe it means that its mass is large enough to slightly perturb the orbit of the outer planets near it, just enough that we can measure those differences. Maybe it means that you have to be so close for your deep space probe to fly by it and get a little gravitational boost out of it. Depends on what you're using the number for. But it's got a meaning, and you should think about it. In fact, you should think about the meaning of a number every time you encounter it, because if you don't pay attention to the meaning, you're not doing physics, just math.